Okay, so 5.4.2 is a theorem that assumes that three parallel lines exist and there are two transversals that cut through them. You'll remember back from previous geometry courses that if you have three parallel lines and a transversal is cut in equal pieces, that those three parallel lines will always cut equal pieces. In this one, we're going to grow the idea just a little bit. And what I've done is I've created three parallel lines here and two transversals. And it's really important here, I'm going to make this point because I've seen it be misused before. This theorem says if three parallel lines intersect two transversals, but three parallel lines are assumed. And so anyway, this theorem says if three parallel lines intersect two transversals, then those transversals are cut proportionally. So the conclusion of this theorem is that in this case, let's change color a little bit, EC relates to CD the same way that BF relates to FG. So that's the conclusion. It seems fairly intuitive maybe to you that no matter how I move these lines, that those pieces will remain constant in the sense of how they relate to each other. Here's the quick proof. There's actually two different ways to look at this one. One is to think about this this figure as almost being a giant triangle, where let's say E and B become the same point. Now what we have is a side splitter theorem where we have a parallel line and a side of the triangle. The triangle is now like, let's say, EDG, and we know that this piece up here is related to this piece down here the same way that this piece is related to that piece. That's not really a great proof, but it's certainly what's happening. And then what we're doing is simply growing these apart, and that those proportions should hold anyway. Nice proof goes something like this. If I connect, if you look down here, connect B to D. Let's mark this point in here as X. Whoops. And now, in fact, what we have with triangle EDB, right, is a side splitter theorem where EC relates to CD the same way that XB relates to XD. Well, we also have this other triangle as well over here. Triangle BDG is a side splitter theorem as well. And we know that BF relates to FG the same way that XB relates to XD. And therefore, here's the nice proof. EC relates to CD the same way that BF relates to FG, which is exactly what we were trying to prove. Let's see if I can erase some of this stuff and just get rid of the junk. Oops, and I erased the proof. But in the end, what we did end up proving was that EC relates to CD the same way that BF relates to FG. Anytime we have three parallel lines intersected by two transversals. One last point. The converse does not work here. In other words, if I have a situation where I have transversals that are cut proportionally, it does not flow that the lines will be parallel. And I'm sure you could come up with a way to show that just because transversals are cut proportionally does not imply that the three lines have to be parallel.